Alrighty. So it is noontime. I know you guys are excited to see each other after not seeing each other for a week. Unfortunately, you also get back to see me too. All right. Well, I hope you guys get a good break and have enough time to have a break from the break. We know how that happens usually. And then we're going to continue with the topic, which is propositional logic. So I'm going to start with this example, which is actually in the notes already. It is called, another example, okay, because there's another one up here that is easier. But I'm going to go with this one today. And it has all the components of propositional calculus, the four tuples. The first one is alpha. So in this case, we have the two constants, 0 and 1, usually use those to mean false and true. But remember, everything in propositional logic here is mechanical. Okay, it is not based on the truth table. It is not based on the definition of the operators. Everything is syntactic. Okay, it is just syntactic. And then we use P, Q, R, S, T as the variables. And then I use rho, phi, and psi as the Greek letters. They're called schematas. So we have constants, two constants, five variables, and three schemata. And we'll actually get to see how schemata are used, later on. And then for omega, which are the operators, we have the usual, we have and, we have or, implication, and logical not. Technically speaking, implication is not really needed because we can define implication by not logical not combined with an or. Okay, so it is not really needed. But from our perspective, from the human perspective, implication is a very useful operator, and that's why it is included. So now we start with iota. Okay, this is one of the things that we have not really talked about is what is iota. Iota are basically iota or elements. Each element of iota is a well-formed formula. And more than that, it is known to be true. In other words, don't ask why, okay? It is just given to you as true. So in this particular case, we have one given as true, and one is a well-formed formula because one is in alpha itself, and as a result, by definition, it is well-formed. Not zero is also well-formed because zero itself is in alpha, so it is well-formed. And then we have a one operand operator, which is logical not, and it only has one single thing to operate on. So as a result, this expression is also well-formed. S or T, the whole thing implies Q is also well formed because S is well formed, T is well formed, S or T is well formed because or requires two operands, and then Q is well formed, and then when we have a well-formed formula on one side of the implication and another well-formed formula on the other side of the implication, then the implication operator is also well-formed. So that's kind of like a recursive definition of what is well-formed. If you use well-formed components and use the right number of operands with the operator, then the resulting expression is also well-formed. So do we have any questions up to this point? Yes? That would not work in propositional logic because it requires quantifiers. So remember, in propositional logic, we cannot handle quantifiers. So in order to work on what you just mentioned, we need predicate logic. So we need a slightly different logic system to handle for all, right? Because you have the universal quantifier in that one. And then the last one, the last element of iota is not Q. So not Q, once again, is well-formed because Q is from alpha. It is by definition well-formed itself. And then the logical not operator requires one single operand, and we are providing that one single operand here. And as a result, not Q is also well-formed. In other words, iota consists of elements that they have to be well-formed formulae to begin with, but these are given to you by definition true to begin with. So there's no derivation required to show anything is true in iota. These are just given to you as quote unquote true. So this time I'm giving you zeta as with it has, let me count. This is one element. This is another element here. This is another element here. This one is a little bit longer. And then we have another element here, and then we have another element here. So every element in zeta has two components. It has this little kind of T symbol that is rotated counterclockwise by 90 degrees. So when you look at the T thing, the one thing you can kind of remember in your head is T stands for transform. Okay, because that's basically what it is. It is also technically called infer. Okay, so we can say the empty set infers psi or not psi. So now the question is, where is that psi coming from? The psi or any of the Greek letters, any of the schemata can bind to any statement that is known to be that is true. Okay, now whether it is true because it's in iota or whether it is derived later on does not matter. Okay, any well-formed formulae. In this case, it doesn't even need to be anything that is known to be true. This can be any well-formed formula. Psi can bind to any well-formed formula. The reason why we have an empty set here is basically saying there's no requirement. Okay, there's nothing that is a requirement. Just find me a well-formed formula, okay, and we'll bind it to psi. And psi, then we can have psi or not psi to be known to be true. Now, does that make sense? Okay, so so out of this entire system, let me see. Okay, I can use the tablet. Give me a second to set up the tablet. And I have to switch the network first. And that will work. Okay. Oh, not working because this one wants to go to the school network, which is not going to work. Give me a second here. Make sure I switch this one to this one. All right. So now that should work. Give me a sec. There we go. Okay. All right. So now I have to backtrack and remember what I was trying to say. Right. Okay. So what I was trying to say is out of this system, okay, just for no particular reason, let's consider this thing here, okay, P and Q, the whole thing, or not R. Okay, is that a well-formed formula under the definition of alpha, omega, and yeah, so between alpha and omega, we can already define what is well-formed. Is this well-formed? It is well-formed. Okay, so what we're going to do is to say, well, since there's no particular requirement, because the left-hand side of the inference or transformation is an empty set. Let me go back to this slide here. Because this is an empty set, it's basically saying, oh, we don't have any particular requirement of pattern matching. Anything can go. So on the other side, we just have to say, okay, find me a well-formed formula. Whether it's true or not does not even matter. It just has to be well-formed. So that means in this case, I can now say, okay, we'll just make psi the same thing as this. It is bound to this particular well-formed formula. So now I can apply that rule. So when we apply the rule or apply the transformation, we just say, okay, give me whatever psi is, and I make a new expression called psi or not psi. Okay, so let me go back to the super note here. So in this case, your psi or not psi is really just a longer version, okay, P and Q or not R on one side because that's psi, and then or the negation of itself. So when I said, with itself, I meant the entire thing. Is that okay? So now I can add this expression back to, and I can now label this one as it's an expression that is true. Now, so does anyone want to challenge this claim that this expression here is true? How do we know it's true? I don't even know what is P, Q, or R. How do we know this whole thing is true? Yes, it leads to a Boolean value, but whatever is on the left-hand side of the OR is negated on this side. And I'm using an OR, so that means one of them has to be true. And because they are combined with the OR, so that means the whole expression has to be true. Yes. Mm-hmm. Mm-hmm. It's well formed. Syntactically, it is well formed, but on top of that, it does not even matter what the values of P, Q, R are. We know the expression that is underlined has to be true. Is that okay? Does everybody kind of understand how a transformation rule is applied? The set on the left-hand side of the T is specifying a requirement. In this case, there's none because it's an empty set. The right-hand side is basically saying, oh, okay, so give me some expressions, okay? Each Greek letter can bind to any well-formed formula as long as they meet the requirement on the left-hand side. In this case, the left-hand side is empty. There's nothing here to specify what the requirements are. So that means I can pick any well-formed formula as my psi, and then I can now combine the psi or not psi to become a new expression, and this new expression is now labeled as true. Is that okay? So that's how we apply these rules. So now what we want to do is to go through this, step by step. So the first step is I look at phi as S or T, okay? Because all we need at this point is for S or T to be well formed. Is S or T well formed? Yeah, okay, that's fairly, obvious. And psi is just Q, is Q well formed? So that's fine. Okay, so picking phi and psi to be these two is fine. So now the question is, okay, but can we fire any particular rule? So in this case, I can fire the rule of the implication rule, which is right here. Okay, this is the implication rule. So this means, now I have this requirement. This particular transformation specifies that I have two requirements. Okay, the first requirement is I need to find an expression that is known to be true, that's an implication, and the left-hand side of the implication is bound to the Greek letter um, phi in this case, and then the right-hand side of the implication is bound to the schemata or the Greek letter as psi. But I also have an extra requirement. I also need the negation of the right-hand side of the implication to be true or somehow proven to be true at this point. So that's the requirement. So the question is, can I do that? So if I bind S or T as phi, which is going to here, and if I bind psi to Q, then I go like, yep, there's an expression exactly like that. Okay, this expression here is exactly like that. But at the same time, I also need not Q to be true because psi already is bound to the expression Q, and the requirement here specifies that not Q also needs to be true. But do we have not Q known to be true at this point? Yes, we do. It is in iota. It is given to you in iota. So in this case, I can now fire this rule because I have met both of the requirements on the left-hand side of this transformation. And then the transformation basically just says, oh, whatever this phi turns out to be, just negate it, and it is now known to be true too. That's how we fire this rule. So from here on, we now can say, oh, the negation of S or T as a whole is also true. Okay, so I'm just going to pause here to make sure that we all understand how a rule is applied. It's really pattern matching. Can I bind the Greek letters in a certain way so that whatever is known to be true at this point of the derivation can work out, with the entire set that I specify on the left-hand side of the inference. So in this case, I have two particular patterns to match. Yep. You okay, so if you replace this side with a zero, you also have to replace this with a zero. So we don't have anything yet at this point that is implying zero, so it won't work because we cannot find that pattern. Yep. Not exactly just I, because we have the all the well-formed formulae, and then of all the well-formed formulae, we label some of those to be true to begin with. Everything in iota are labeled to be true. And then we have an infinite number of well-formed formulae that are not labeled initially. So what we are doing here is, every time we fire a rule, we are labeling one of the well-formed formulae in the entire space of all well-formed formulae to be, oh, we can label this one to be true as well. Yep. Is what? Is, say again? Equivalent? They are not equivalent. They are axiomatically true. In other words, you cannot argue whether they are true or not. They are just given to you as true. So in this case, it is kind of interesting because I never said anything about PQRST individually as variables, whether they are true or not. I am simply saying that S or T, the whole thing implies Q as an expression is true. Now, don't ask me why that is true, okay? It is just given to you as true. I'm also just saying that the negation of Q is true. Now, this one is kind of, you can argue and go like, oh, so that means your Q is false. Yes, okay. But, you can have any expressions in iota, and they are just axiomatically true. Are we still doing okay so far? Yes, go ahead. So with the first transformation in zeta, or the first one that is listed, okay, I have to be careful because in the set, elements are not really sorted. So the first one that is actually listed here is basically specifying that there's no particular requirement in terms of what psi can bind to. So psi can bind to any well-formed formula. Whatever psi binds to may be true, may not be true, may not be known whether true or not. It does not matter. So the left-hand side of the inference is basically specifying as a certain type of pattern to match. So when it is an empty set, it means there's no requirement whatsoever, which also means the schemata can now be bound to any well-formed formulae in the entire space. Yes. Okay, can you rephrase the question a little bit? So everything is in iota is given. Okay, you don't question why those things are true because they're just known to be true. Okay. Uh-huh. So the mechanism is completely syntactic. We do not use logic here. So this is a completely syntactic operation. So when we evaluate this particular rule in Zeta, we're basically asking the question of can I find can I find phi and psi such that both of these patterns can be met at the same time? So now we go like, okay, let me see. If I bind phi to be S or T, if I bind psi to be just Q, then I can meet both of these pattern requirements at the same time. So all the requirements in the set to the left-hand side of this transformation are met at the same time, which means I can now fire the rule, okay, quote unquote, fire the rule. When we fire a rule, all we are doing is to say, oh, whatever pattern is matching phi, the negation of that can now be labeled as true. So when I say labeled as true, it simply means just labeling, okay? Because we have a space, an infinitely large space of well-formed formulae, and certain ones are labeled to be true to begin with. Basically, anything in iota are labeled to be true to begin with. So our objective is to try to label other ones to be true and see if we can prove a particular expression to be true as a result of iota or not. That is the objective. Is that okay? All right. So, yeah, go ahead. It is not axiomatic, but nonetheless, it is true. Yep. So everything in iota do not need any application of the rules in Zeta to be true because they're just known to be true, but other ones can be labeled true as a result of the rules in Zeta. So at this point, after this particular application, so now we label the negation of S or T to be true. So now we have one more well-formed formula in the entire space of well-formed formulae to be quote unquote labeled true. So now it can be used to fire additional rules. Correct. So in this case, it is already this is a really small subset compared to all the transformation rules that I show you guys in Wikipedia. So this is already like, really, really pared down. The human system has like 20 something rules and they all have, strange Greek names, okay? Because I don't speak Greek, so they're all strange to me. Um, and it's really difficult to remember the applicable rules to begin with. And then even if you can remember all the applicable rules, at any given time, there's a certain number of rules that are ready to fire. So which one do you choose to fire? Some you can fire as many times as you want, and it doesn't get you anywhere, right? And then some may actually lead you to the statement that you need to prove to be true. But because the space itself is infinitely large, just because you have cannot label the expression that you want to label yet does not mean that it cannot be labeled. But when do you give up and go like, okay, I don't think there's a way to label this thing to be true? There's no way to tell because you have an infinitely large haystack. You can never conclude whether the needle is actually in the haystack or not. So that's kind of the discussion of why this particular system is problematic. But it is nonetheless, the original formal logic system, that the Greek philosophers came up with. So it provides a backdrop of what we are ultimately going to do in a much more mechanical way. Okay. Yes.